All right, let's see here. We're going to switch over to Paint for a video on, well, I guess you know it's a video because you're watching this, on vectors, specifically now with the components of vectors and finding what's called a resultant vector, okay? So this video hopefully is a good little practice for you, refresher if you're kind of rusty on this or maybe need some more talking through it, which, hey, nothing wrong with that. Physics can be hard. So let's do an object. And again, we're going to make this simple, okay? This could get way, way harder. You'll learn when you do physics, you basically learn like little baby steps where you go up the staircase of scary, okay? And the first couple steps, right, we're knowing that we got to do more stuff, right? So if you do this problem in the real world, it's not as simple as this, but it's a very good start to it. It's an approximation, and it gives you an understanding of vectors, which of course you'll be using a lot in physics. So something you really need to have down, okay? And we can make it more complex, right? As we get into more forces, as we get into more types of forces and whatnot, we can of course start to add those things in and make it more complex. So imagine you're doing like steps 1, 2, and 3. You know that steps 4, 5, and 6 can change your answer, but these are the beginning ideas. Okay, so hopefully you're saying, okay, I kind of get it. And what I'm going to do with this box is I'm going to say, let's have a force, and I don't know, let's make the force, make it easy. Let's make this force perfectly perpendicular, normal to the box. So if I can get this to make it look nice and pretty, there we go. I guess that's good. And this force is pushing down, right? So let me change the size of this. Okay, so I'm going to, and my mouse here is not the best mouse, so hopefully this is not too bad. Okay, this one force here, I don't know how many newtons of force. I don't know. Let's make it nice. Let's make it 1,000 newtons. Okay, and it's pushing straight up and down. To be technical, right? To make sure we're on the same page, you'd want to make sure you know that. So you would be looking for maybe this symbol, right? That symbol means a square angle, a right angle. Okay, so that means it's perpendicular. Yay, and we like that. Why do we like that, you might say? Because when it's a right angle, or any derivation of a right angle, aka 0, 90, 180, 270, 360, going around the full circle, the full unit circle, those are nice because sine and cosine, their behavior is they basically switch from 1, 0 to -1, okay? Sine and cosine, their outputs are always between, their range is always between +1 and -1. Okay, now you can do things to make them bigger and smaller, but what I'm saying is if you just see sine, okay, just sine of x, it's always going to be between 1 and -1. Okay, cosine, same thing, 1 and -1. Tangent is not going to do that. Tangent could be negative infinity or negative infinity, positive infinity. Okay, but that's yeah, let's not make this too scary, okay? So we like it though because now this angle is basically straight up and down, which means the components of this vector, if you visualize this as a triangle, you're like, it's a triangle that has no base. It's a triangle that's just height. Exactly, because sine of 90 is 1. Okay, and cosine of 90 is 0. All right, which means there is no x, which makes sense because this force is pushing straight down. Okay, it gets harder when, of course, the angle begins to become more acute or more obtuse. Okay, as we approach 180 or approach 0. Okay, anyway, you're probably saying, I know that. Why are you spending so much time? Because this problem isn't too bad until maybe I throw in a force that's coming in at an angle, right? And again, this should not be anything new to you, but this video, maybe it's your first time ever seeing it. Maybe you're like, oh, I'm going to watch this video in 2033, and you're going, wow, Mr. Carroll looks a lot younger. I don't know. In any case, this force here, I don't know, let's make this 1,000. Why not, right? I'm just making up numbers here. Okay, and that's fine. The angle, though, we need to know the angle, and this is where things can get messy, okay? Because when you do these angles, you got to be thinking, let's do, I don't know, what's a good color for this? I don't know, purple, sure. When we do the angles, we need to know with reference to what, okay? Because if you think about it, right, this triangle is pushing to the left, if you picture it, right? And it's pushing up, okay? So you have two angles, all right? This is the right angle, of course. That's not an angle we can use, okay? We could use this angle or this angle. And the trick is, depending on what I give you, you need to know what to do with it, okay? So generally speaking, not always, but generally, you'll be given an angle with reference to the object. And because it's hitting the side here, you can basically picture it's hitting the y-axis. So this angle here is in reference to the y-axis, right? We're using the y-axis as our angle reference, okay, if that makes sense. Okay, and let's say this angle here, I don't know, let's say 35 degrees. Why not? 35 degrees, okay? That's important because it means if this is 35, we could easily find this angle, right? 90 minus 35 would be 55 because the interior angles of a triangle have to sum to 180. This is a 90-degree angle. 90 plus 35 is 125. Ergo, this would have to be 55. Okay, some basic geometry, some basic trigonometry. Okay, the angle you use matters a lot. Okay, because when you do your trig later, when you do your sine and cosine or tangent, which angle you pick matters. If you do 35 or you do 55, you can use either one, but you have to be consistent. Because if you don't know what happens to sine and cosine when you change from y-axis to x-axis, you're going to have a bad day. All right, very easily mix this problem up, and you're going to be very sad about that. So please don't do that. Let's make this problem even harder. Let's do another one, right? As harder is not, it's not that bad, but let's do one more maybe. And let's say this one is, I don't know. Let's say it's coming in, and it's coming in here, hitting the bottom of the object. It's worth noting again, as I said, when you do these problems, you might be saying, what about gravity? Doesn't gravity affect this? Again, we're kind of assuming this is like in space, perhaps, right? This object is floating in space. There's no gravity in this environment, right? Very little gravity, so little we ignore it, okay? Because if we did it on Earth, yeah, we'd have to have a vector pointing down, which would be weight. We would need the normal force, assuming it's on something. We would need to have those, but again, we're getting at ourselves, okay? This force, I don't know, let's make it 1,000 again, or no, let's make it 500. Why not? I don't know. I'll change it up a little bit. 500 newtons. And the angle, again, usually, not always, could be given in reference to the y-axis, okay? And it matters which way, right? So in this case, or I'm sorry, to the x-axis, my apologies, to the x-axis, okay? Could we do to the y? Could we imagine that there's a y-axis here? Absolutely we could, right? And then we could get this angle. Okay, you could certainly do that. Nothing wrong with that, right? But I'm just trying to show you how to think these things through, okay? So then that angle, let's see. Let's do 45. 45 is a nice number. You'll see why in a minute. 45 degrees. Oops, that's horrible. Let's try that again. I got to get one of those writing tablet things. You know, you can write and show them on the screen. That'd be nice. And I ask you this question. I say, what is the resultant vector? When I say resultant vector, what I'm getting at is that these three things, these three objects pushing, or you could even imagine as strings pulling from the opposite side, but let's not make it too bad. Basically, what's going to happen? Because you look at this, you're not immediately saying, I know it's going to go in this direction. You have to figure out that these three vectors, okay, you can't just add them together because they have angles. You can't just say, oh, that one's bigger, it's going to win. Well, the angle is going to make a difference, right? Is it pushing completely horizontal? Is it pushing completely vertical? Usually not, so you can't just eyeball it. And this is where a free body diagram is going to be your best friend, okay? So my free body diagram, I usually draw it as a square, okay? This problem, again, is a square, right, or a rectangle, right? So you might be saying, it looks like the same thing to me. Yeah, it could be a car I'm drawing. It could be a boat. It could be anything. The free body diagram just distills it down to a simple box. Most people do circles. That's fine. Whatever. I prefer the box. Okay, you pick what works for you. And what we're going to find out is my vectors, what are their components? So if I name these, right, sometimes they're named for you, right? I could call this the red vector, the orange vector, the green vector, or the blue vector. Or you could just call this, maybe this is F1. This is maybe F2. And then this, of course, would be vector 3, F3, right? Force 3. Okay. Does it matter which one's 1, 2, and 3? Not really, right? I mean, we could have done blue, orange, red. It doesn't make a difference. But what matters is now you have names. Why are names important? Because then I can start to think, where are these going? Like if I were to break down these triangles, these vectors into triangles, where are their components going? Okay, we already did F2, right? If you think about it, this would be, let me change colors here. I guess we'll change, I don't know, to orange again. Sure, why not? This is F2, the hypotenuse. The x component, this would be F2x, okay? And then the y component, the up-down component, would be over here, the height of the triangle. That would be F2y. Oops, that's really ugly, F2y. Okay, so I have those two. Those are the components of the vector. Okay, the components of the red vector, as we already said, it's a right angle. There is no base, which means this is the same thing as F1y. Okay, vector F1, it's up down. It's entirely vertical, entirely in the y. Okay, so you're like, oh, okay. And then vector 3, the blue guy, right? We're looking at that. I guess we should draw our triangle, right? So we have maybe up and to the right. Okay. And then, of course, the numbers, or the names, I should say. This is your up-down. This would be F3y. And then this would be F3x. It's really hard to draw like this with the mouse. Okay, so now you say, okay, cool, why did I do that? Because now I can put it on my free body diagram. Okay, so I take these three vectors. I should is the key word, not always, but usually, see 6 vectors, 6 components of the vectors on this free body diagram. I say should in this case because remember, vector 1, F1, only has y. There is no x. So do I have to put an x on for F1? No, it's 0, which means what? Left 0, right 0? It doesn't, if you really want to put one, I guess you could, but kind of silly. So what do I do then? I say vector F1 is pushing down, okay? And this one's actually nice because I actually happen to know the value, right? This is nice because if I did the math, sine of 90 times 1,000 is going to be 1,000. Pretty nice, okay? So I can say this is vector F1 y, and I happen to know the value. Okay, so I could come in here and say, let me just type it so it's going to be easier to see. This happens to be, oops, not 100, 1,000 newtons. Okay, it's pushing down. Okay, you might say, how come it's not negative? Well, because the arrow tells me it's down. That means it's negative. Okay, remember the arrow is kind of the sign with the number. If you don't have an arrow, if it's just a number by itself, then you have to have 1,000 newtons. Okay, well, let me rephrase that. If it's F1y, okay, I should be careful there. Not F1 technically. Okay, vector 2, we got what? 2x and 2y, and it's pushing up. We can see that from the arrow, and it's pushing to the left. So I can say that vector 2, that's F2y. We don't know the value, right? So I don't know what it is. I leave it as just F2y. And then F2x is pushing to the left. Okay, F2x. Okay, I know it's kind of, I guess let me rewrite it. It's a little bit neater, hopefully. F2x, hopefully you can see it. Okay, and that is the vector. Okay, and then finally vector 3, F3, it is pushing up. And again, we would have to do F3x, or I'm sorry, F3y, sorry. You can see how it's very easy to talk oneself silly here. F3y. And it's pushing to the right, okay, as we can see. So that'd be F3x, okay? And basically this gives you a game plan. I need to find these numbers. I need to find F1y. Thankfully, I already have that. That's work done. That's nice. I got to find F2x, F2y, F3x, F3y. Got to find them. So you see, how do I do that? Well, we do some trigonometry. Okay, so let me move this over here. And I don't care where you start, you pick one. I would recommend drawing your triangle. Okay, so what I'm going to do, I'll be fancy here. I actually have a little tool here that can let me draw a triangle. So let's see, I have vector 3, I think will be easy to do first. So I got them blue. Oh, hang on. I got to start lower, I suppose. So I start, is it going to let me draw the right angle there? It's not. Can I rotate it? Let me see. Oh, I can't rotate it. Do I have an upside down triangle? This is what you're coming here for, right? Is me trying to figure out why Paint won't let me flip it. Well, I'll just draw it then. That's fine. I don't care. It doesn't bother me. So it's going like this, and it's going to the right, and it's going up. Okay, here's my right angle. Yay. Just helps to draw it outside here. You don't have to. I just think it might help. Okay. And I have this value here, 500 newtons. And then, you know, the angles, again, the names you give them is kind of up to you. I generally think the angle you're given first should be theta. It doesn't really matter. You can call it Steve and Ralph, right? But the angle we're given here is 45. 45 is a very nice angle, okay? Because you might be saying, I know what's going to happen. If this is 45, well, necessarily this has to be 45. Why? Because 45 plus 45 is 90, and 90 plus 90 is 180. Hey, right triangle, yay. This is a, I guess what would you call that? An isosceles right triangle, is that right? I think. I don't know. It's been a long time since I've taken geometry. But it has two equal sides, which means that f2x, once you find it, it has to be the same as f2y. Okay, so we find one, it's a 2-for-1 deal, which we love. We love 2-for-1 deals. Okay, so two 45-degree angles. And you say, okay, I kind of get it that the angles are the same, but why do these have to be the same? You're just saying that. Well, if you do sine of 45, so I'll type that so you can see it better here instead of me drawing that out. If I do write sine of 45, and I multiply this by the vector itself, in this case 500 newtons, I will get what? This is me, I've done some algebra to get this to work, right? And again, if you're taking physics, presumably you understand how I got this. If you don't, you need to ask, okay? I don't want to keep these videos short. The algebra steps, hopefully you're clear on, right? How I got the 500 over there, okay? Opposite over hypotenuse, I brought the hypotenuse over, okay? Is equal to, in this case, what? Well, which angle do I use? Okay, in this case, it doesn't matter because it'll be the same answer either way. But if I'm using this angle right here, I don't know if you guys can see what I'm hovering, the angle that we were given, the opposite side would be f3y, the adjacent side would be f3x. Okay, so if I do it this way, I'm finding f2y, all right? And sine of 45 is like 0.707, I think. By the way, a good thing to note, make sure your calculator is in degrees. If it's in radians or gradians, it will not work. Or it'll work, but you'll get an answer that's wrong. Okay, so make sure it's in degrees, right? So I say 45, I say give me sine, hey, 0.707, look at that, times, it's a pretty famous number. That's not that impressive, right? I mean, it's pretty useful to know. Times 500, and I hit enter and it doesn't work. I get 353.55. I'm going to round to the hundreds place here. So what did I get? 353.55. 353.55. 353.55 newtons. And hopefully you're saying, I know it's positive. You say the answer is positive. What do you mean I know it's positive? Well, it is positive. Should it be positive? Should I keep it positive? Should I make it negative? Well, 3y is pushing up, so that should keep this positive. Okay, so that's good. That is f3y. And then I could repeat this calculation with cosine of 45. And incidentally, if you don't believe me, if you're like, you're lying, if you check, cosine of 45 will also be 0.707. So if you're like, prove it to me, well, let's do it. 45, take a cosine. Hey, look at that. It's the same. It's like magic. Times 500. And it's going to be the same answer, right? So I don't know why I'm doing times 500, but whatever. We'll do the full steps. We get the 353.55, okay? So this was, oops, I clicked out of it. Now I got to type it here, I guess. Whatever. 353.55 newtons. Hey, is this negative or positive? According to this, it's positive, right? It's pushing to the right, so I will keep it positive. Okay. Good. All right. Hey, those are my components. If I want to put them in the free body diagram, I can. All right. You can put them back in there if you wish. It's up to you. Okay. But then let's do our next one. Okay, our next one is going to be vector 2. And for that one, I don't know, will this work for the triangle? Let's see. I guess switch to orange, don't I? Hey, it'll work. Look at that. Okay, nice. Hey, saving time. Perfect. All right, and my 1,000 newtons here. Awesome. And then this right here would be F2, oops, I should do the underscore, F2 Y. And this would be, oops, come on, click. Why aren't you clicking? It's not clicking. Click. There you go. I don't know why I was doing that. f2x, okay? Again, this is notation. It's how you write things, how I write it. Okay, I usually do the underscore underscore to make it f2x, but again, it's not the end of the world. All right, and my angle, we're looking here relative to the y-axis of 35. So 35 degrees. Wow, that looks horrible. Let's try that again. 35. That looks, I spoke too soon. Looks better. And then this angle here would be, I suppose I should use this symbol, right, for angle. Well, now it looks like less than. I don't know if I like that. I don't like that. And this would be 55. Okay. And you got options here, right? Do you want to use 55 or do you want to use 35? And you say, what's the difference? Well, take a look. If you use 55, the opposite is y. The adjacent is x. If you use 35, the angle given, they're flipped. So now the opposite would be x and the adjacent would be y. All right, so if you look, opposite x, adjacent y. All this means is you pick one and you have to make sure you know, am I using sine or cosine? And that's why drawing these things out helps, because then you're less likely to make a mistake. Okay. In any case, let's do the calculation. Show, let's go ahead and use 35 because that was the thing we're given, right? So now if I do cosine of 35 and I multiply this by the vector, which is 1,000 newtons, I will get y, okay? Because it is the opposite, I'm sorry, it is the adjacent, right? I use cosine, the adjacent divided by the hypotenuse, okay? This will be y, all right? Show, there we go. So what is that? I don't know. Top of my head, I don't know what cosine of 35 is. So we say, hey, computer, you do the work for me, Mr. Calculator. Cosine times 1,000. And we get, what, 811 or 819.15. 819.15. 819.15 newtons. Now you got to ask yourself, is it positive or negative? Should I keep it positive is a better question. It's pushing to the left, okay? Well, actually, let's back up. Is it up or down? See, even yeah, you can see how easily this happens. Is it up or down? This is y. Is it up or down? And you say it's up. Hey, let's keep it positive. Cool, okay? You got to have these internal little conversations with yourself. Sound like a crazy person because you have to make sure you know, oh, that's y, and should it be positive? If you really want to do it a way where the math does it for you, then you need to rethink how you're getting your angles, okay? And there's a way to do that if you really want to. You're like, I want the math to come out negative when it's left or down. There's a way to do it. I might make a video about that. It's not like it's that hard. I just think it doesn't really save you any time. I don't really know. I don't think it's going to help you. If you're a programmer, then it might help you, I suppose. Like if you're programming something that does vectors, maybe. But I don't think. Yeah, that's just an opinion. So this is positive, yay. And then let's get we'll get sine of 35. This will be now for x, right? Because the angle we're using times 1,000 newtons, and it'll be smaller, right? So let's see how much smaller. 35. Excuse me. Take sine. Yeah, a lot smaller. Times 1,000. 573.57. Wow. Oh, 353. I was like, that number sounds familiar. 573.58 if we're rounding. 573.58. 58 newtons. And now you say, should I keep this positive or negative? Well, it's pushing to the left, so I should make this negative. Oops, that's 1. Negative. Okay. Now, technically, the equation I just wrote is technically wrong because that's right. We got a positive number, but we are making it negative because we know it's pushing left. Okay. That's the point. So now you got your numbers, right? We have 6 numbers. We have y has already been found. That's 1,000. And we have f3y. We have f3x. We have f2y. And we have f2x, okay? And now comes the part I guess you've all been waiting for, which is the resultant vector. So what I will do is I will erase this, I suppose. And if you need this, just pause and go back, right? I mean, it's, like you can always pause this and go back. It's a video. It's nice. Delete. There we go. Okay. So I'm going to come up here. And I'm going to take what's called the sum of forces. Okay, it looks like this. So I would say, hey, the sum of the forces in the y direction, that is equivalent to what's called F net y. Net means when you take everything into account in the y direction, what is the force? That's basically what it is. Okay, what does that look like then? And this is where the positives and negatives matter big time. Okay, I have negative 1,000. That's my vector 3, right? Or I'm sorry, vector 1. Sorry. Ugh, it's been a long day. Let's switch colors. You can even maybe visualize this better, right? We have a negative 1,000. Let me switch the size. Negative 1,000 newtons because it's down. Plus, what? We got 819.15. That's vector 2 in the y. That's positive. Yay. Newtons. Plus vector 3 in the y, which we said was positive 353. Oh, I didn't switch colors, did I? I'm being silly. Orange, and that was 819.15 newtons. Plus, and then we got vector 3, which we had as 353.55 newtons. That's kind of nice to have the colors, right? Makes it a little easier to visualize. Those are the things, okay. And we plug them in a calculator, because I'm not doing mental math like that, because that's a lot of work. Not a lot of work, just annoying, right? What do we got then? Negative 1,000 plus 819.15 plus 353.55. And we get positive 172.7. Very important, positive or negative. In this case, positive, which means this thing is going up. Okay, that's good. So I can take that and say equals positive 172.7, I believe, right, newtons. Am I right? I think. Yay. That's why. Cool. And I do the same thing now, of course, for x. Same exact thing, just now it's in the x direction. So now I have the sum of the forces in the x direction is F net x. Okay, I should put my vector arrows to be consistent. Although some people don't put them there, but I think I don't know. It's a vector. I think you should include it, right? Anyway. And my numbers, what do I got? I guess I'll do the color thing again, right? Because that was cool. Red, vector 1, has none. So technically, we'll be technical here, right? If you really want, we would say 0 newtons, right? That's the vector 1, no newtons in the x, okay? Plus, vector 2 is pushing to the left. That was our negative. So it's plus, I'll put in parentheses. Well, I'll just put it like this. I'll just change it. Plus negative, same thing as minus 573. Oops. Why is it? Is that in? It's so similar, isn't it? This orange is very similar color. Anyway, minus 573. It almost looks red to me. It's weird. 573.58. Plus, and then we switch to blue. This is going to the right, so it's still positive. Plus 353.55 newtons. And we say equals. We can tell it's going to be negative, right? Looking at this, we know negative 573 is bigger, but let's get the exact amount. Again, calculators are your friend until they aren't, because sometimes calculators can be mean. If you know what I mean. Haha. There's a joke in there because mean means average, so on average they're 9. Anyway. All right, 55 minus 573.58. I just flipped it so it just the negatives work out. Negative 220.03. Negative 220.03 newtons. And hey, that means it's going to the left. Okay. So, cool, we now have these two net forces. And that is nice because then what we can do is combine them to make what's called the resultant vector. Yay. All that work to figure out, hey, what's the resultant vector? Okay. And for that, let me erase, I guess, my free body diagram. I guess we're done with that for now. So I'll take all that and say bye-bye. So I have some space. And now let's think about this. So my net forces, I have positive 172.7. So if I think about it, I'm going up, 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 up. This thing is going to go up in the y-axis, right? And then I have, what, negative 220.03, which means I'm going to the Okay. Now, if you draw the triangle like this, you might be like, up and to the left, up and to the right. Which way am I going? Right. This is good because I can draw my arrow here, right? I kind of talked myself in a corner there for a second, right? We are going up and we're going to the left. So this arrow is telling us the direction we're going. My x is negative, my y is positive. What I was going to say for a second is how you draw this matters. So if I say we're going like this, then you might be like, down and to the left or up and to the right, right? It's at the end of the day, it really doesn't actually matter, but I would recommend for your own sanity to draw it in the way it's going to go. It's going up and to the left, okay? When you get this, you say, okay, I like it. Right angle here, angle theta here, angle phi here. Generally speaking, I'm not saying always, I'm not trying to say like, oh, it's never done the other way. You would like the angle that is in reference to the object, right? This would be in relation to the, like if you visualize this relative to like the ground perhaps, or like relative to some y-axis that is off the object. You could do it, okay? But I'd probably recommend using this angle. Could you use this angle? Sure, why not? But probably easier to use this angle here, okay? Imagine the object is here. We're saying the object is going that way, okay? And if you picture it, here's the object perhaps, right? You could say, this angle here as well, right? Does it kind of make sense? Okay, in this case, we have an arbitrary x-axis we're drawing off the object. In this case, we have in reference to the object off the y-axis. This is probably the part you're going, huh? This is where it gets confusing, right? I mean, what angle do you want to pick? This one, this one, this one? And truthfully, because you can draw triangles however you want, there really is no, let me say this carefully, there's no wrong answer, but there's probably better answers, okay? So if you pick this angle here, just make sure it's clear how it's described. Do you draw the picture? Do you describe it? Do you say off of the y-axis of the object, right? Do you say off the x-axis of the object, right? It can be a little messy. In any case, we want to know what is the value of that. So let me erase all this, I guess, right? We want to know what is the value of that, and say, how do I do that? Well, we just found, if you think about it, this is the y, and this is the x, right? So you say, oh, I see. So now I have what? Negative 220.03. Now, it says negative. Because we have arrows, we can treat this as positive. Is it against the law to make it negative? No, it's just that because we know it's going to the left, the arrow denotes that, we can leave it as positive, okay? And when we do the math to it, interestingly enough, when you do your math here, it being negative or positive ends up not mattering much, believe it or not. The important thing is you know it's going to the left, okay? And then, of course, the positive going up here, right? That's our, what, 172.7? 7 newtons. Okay, and hopefully you're saying, hey, this looks like a Pythagorean theorem problem. Yeah, you could certainly do it that way. A squared plus b squared is c squared. Base squared plus height squared equals hypotenuse squared. Okay, so let's do it. I will do the radicand first. So what's in the radical, I'll do that first. I think that's called a radicand. It's been a long time since I've taken math and remembers the name of that. I think that's right. I think that's the radicand, I think. And then the index is the thing, right? Like square root, cube root, I think. Hopefully I'm right. The thing under the radical. So we'll do that first on this calculator. What does it look like? 220.03, oops, squared. And you might say, hey, what if it's negative? Well, this is where it doesn't matter, right? Because if you square any number, it becomes positive. Unless it's I, but don't worry about that. Plus, what then? 172.7. Is it 7? Oh, this is supposed to be 7, isn't it? 7. There we go. I must have mistyped it. 0.7 squared. That's not the answer. What do I have to do? Take the square root. Taking the square root, you could do the square root button, or you could be fancy, and you could say raise this to the half power. Half power is the same thing as the square root, in case you didn't know. Okay, and I get in this case 279.71. So 279. Was it 71? 0.71. Awesome. Newtons. And make sure, of course, hopefully you're going to get the right answer, one way to make sure of it, or one way to guarantee that you're not wrong, or okay, that's a horrible sentence. One way to be confident you're not wrong is that your hypotenuse has to be bigger than any one side of the triangle, right? So this is a good sign, 279.71. Now you say, how do we do the angle, right? Again, this angle business, which one do I pick? Let's say I pick this angle here, call it angle theta. What does it look like mathematically? I have options, okay? I'll show you two options. You'll say, hey, they both work. And I'll say, yeah, exactly. Technically, you have three options, but that's a whole other. Well, actually, you have more than three. There's many more, but three that are common. Okay. I think the easiest way would be to say, take tangent of theta. I'm going to write theta because I don't have the symbol theta here. Tangent of theta. Well, that's the same thing as what? The opposite over the hypotenuse. What is the opposite of angle theta here? 172.7 divided by the adjacent, which in this case is 220.03. Notice the newtons cancel. I haven't written them, but they would cancel out. Angles are technically dimensionless. This will be very important later in physics. Okay, angles do not have dimension. But in any case, how do you solve it then? You say, what do I do? You take what's called arctan. Arctan is inverse tangent. It undoes tangent. Okay, and if you're like, why do you have to do that? Well, hopefully you're saying, of course, because tangent's a function. And if I'm doing a function to some variable and I want to undo it, I have to do the inverse operation, the inverse function. The inverse function of tangent is arctangent, okay? Not cotangent. Cotangent is different. Do not mix up cotangent with arctangent. They are different, okay? So let's see what that is. So I'll do the quotient first. I'll do the division. So 172.7 divided by 220.03. That's that. And then I say, take that number, computer, and give me arctan. And arctan, let's see, do I have to do second, I think? Uh-oh. Oh, no. Is this calculator going to be a pain to me? Is it? Oh, I think if I hold tangent, let me see, am I right? No, that's not right. Okay, tell you what I'll do for you here. I'll show you this. Desmos. Yeah, just so you can see it better. So now I have arctan of, what was the number? I don't remember. 172.7? Wow. Nope, that's not right. 172.7 divided by, what is it, 220.03, I think? Let's see. Oops, that's the wrong button. I don't like you clicking that. 0.03, hey, we got it. Awesome. All right, put that in parentheses. One thing to make sure of if you use Desmos is please make sure, and it's going to sound crazy, make sure it's in degrees, because you can see here, wow, those answers are very different. Okay, if you use radians or degrees, is a big difference. We want degrees in this case. We will use radians eventually in physics, FYI, okay? But degrees, and I get 38.13 degrees. Okay, which means that this angle theta is that angle, 38 point whatever I just said, and then this angle, of course, would be 90 minus that, okay? And if you wanted this angle, if you're like, you know what, I kind of prefer this angle here, but what would you do? It would be the same angle as this, okay? This angle and this angle are congruent. Why? Well, if you think about this diagonal, okay, if you do a diagonal in a quadrilateral, the angles that are opposite sides here, right, that are like a cat, what do you call that, cat corner? I don't remember the term, right? But if you have it, angle here are congruent, okay, assuming that it's a regular, you know, that it's a rectangle or a square or whatnot, okay? Yay. All right, and the proof of that, of course, is, hey, this is a right angle, half of the right, or not half, but this portion of the right angle, these two would have to sum to 90. Okay, so you have options. Okay, and if you're picturing, what does all this mean? We've done all this work, all this colors. It's like rainbow vomit on the screen. What do I do with all this? Well, let's picture what I've kind of just done. All this work is to say that that box we drew in the very beginning, right? This box with three forces is essentially doing what now? It is, if you think about it, doing this behavior. Okay. This vector, oops, that's not a vector, this vector are combining to say this box, if assuming there's nothing else acting on it, would go with a force of, what did we say? What did we have for our Pythagorean theorem? I think we said 279, whatever it was. I think it's right here, right? That would be our value. I guess I should Oh boy, do I have to erase all that? I blocked it. 279.71, right? So I guess I'll draw it again. Sorry. You can tell how long a day it's been for me. I'm tired, man. Anyway, we're almost done. Box, yay. Vector, yay. 279 point. Oh no, 279 point. What did I say? 20, I think. Pause the video. You can make fun of me if I'm wrong. And then the angle, we found this angle. It might make more sense to use this angle, right? Because it's on the object. If you use this angle, the one we originally were talking about, that would be, oops, that's horrible. That would be off of what we basically consider to be, here, I'll draw it a little better this time, sorry. Basically off of, if you picture from the center of the object, what the x-axis would be. So if you picture that angle there, this angle here is off the object. It might be a little bit easier to picture that, but it's up to you. Okay. And again, the name of the game is understanding. It's not about like I can find this number. If it doesn't mean anything to you, then what are we doing? Right? We don't learn things just to, like, I don't know, like put numbers in a box and say right or wrong. It's understanding. Okay. Hopefully that makes sense. Long problem. And maybe what I'll do is have some more problems with maybe some more complex conditions here as we get further along with this, because this is not something you just see once and never again, right? Cornerstone of physics right here, okay? One of the cornerstones. So hope that was educational. Hopefully you're saying, hey, that's cool. Or at the very least, you're not going, oh my God, this is scary, okay? All right, so with that said, we will close this video out. You have a great rest of your day. Enjoy.